Okay, so we're back talking about section 1.7 in your college algebra class. 1.7 is the inequality section. There's three types of inequalities that we're going to study. The linears, which was in the last video, then quadratics for this section, and then rational, the fraction inequalities, and each has kind of special rules. So kind of in review, the linear inequalities, you solve them just like you do linear equations, except if you divide or multiply by negative, it will flip the inequality sign from a less than to a greater than, or vice versa. All right, so moving on to the quadratic inequalities. A quadratic inequality means it's going to have a quadratic involve a second degree equation. Whenever x is squared, you've got a quadratic. So we have different rules for quadratic inequalities. To solve a quadratic inequality is really two steps, and you'll see that in your book as well. It's it says threes, but the third is kind of the test. But anyway, let's go through the steps. It's a step process. Step one is just solve the quadratic like you were solving quadratics before. So we'll solve this, pretending it's an equal sign. We could just solve this by factoring the formula, completing the square, and square root property. Remember, there's four methods for solving a quadratic. So pick your favorite method. If you say, I just love to use the quadratic formula and I don't want to do any of that factoring, that's fine. Always use the formula. That's fine. But this one does factor. A lot of these will be factorable, so you'll be able to, if you want to take the time to do it that way. It does do the reverse of the FOIL. Then we set each part equal to 0. And we get two boundary lines, or what would have been the solutions if it was an equal sign. If this was an equation, that would be it. We would be done. But because it's an inequality, we have these next two steps, follow-up steps. So once you get these, that really only makes a boundary line. It cuts your number line into those two spots there. At -3, it cuts the number line, and at +4. Creating three regions, 1, 2, 3 regions. And then you have to figure out by testing, taking test points, sample points along each part of this in each region to see which parts work to solve the less than 0 inequality. So once you know your boundary lines, and again we found it to be +4 and -3, and I wanted to put those in order on the number line. Oh, I shouldn't probably have erased that. I need to have the less than. I just need to know that I'm trying to do the less than 0. The original problem asks you when it is less than 0. So I take a test point in each region. Like over here in negative infinity land up to -3, pick a number, any number in that region. So let's say you pick -2. I think that's what they show in your book. On the next page, they show something out of each. Oh, sorry, -4, I should say. Not bad. So something past -3, which would be like -4, -5, and so on. So they take something out of this region, and they did use -4, and then they test it and see if it works. So we plug -4 in for all of these x's, and we hit it on our calculator, if you like. That'd be 16 plus 4 minus 12, 20 minus 12, that's 8. And you're asking, is 8 less than 0? And no, it is not. 8 is not less than 0, so that region is false. That means anything like -4 or anything else in that region should also give you the same result, that it doesn't work. It does not solve it. So I won't be shading that in. So then I move to the next region. Between -3 and 4, there's a nice number 0 that's easy to work with, so I'll test 0. So we go back through this in the original problem, and you plug in 0 for your x's. And then you crunch those numbers, 0 squared minus 0 minus 12, will be -12. And you say, is that less than 0? Yes, -12 is less than 0. So this time it's true, which infers that any other test point that you would have chosen out of that region would also work. So that's where your solution set is. So we're going to shade that region. And you can test other points if you want to be sure. But if your boundaries are right and you pick something, any one thing out of the region, the rest of the region should also have the same result. So now I'm going to take a test point over here, like +5, 6, or anything past 4. Plug it back in the original problem. 5 squared minus 5 minus 12. And see if that's so. Let's see, I think that comes out to be 8. Again, 8 less than 0. You know, we saw one like that earlier, and it's just not true. 8 is not less than 0, so our test point fails, so I don't shade that region. So your answer, your solution set are the regions that you take a test point and it works in the problem. We're trying to solve this, what works in this problem. So anything between -3 and 4 works. So that is our answer. From -3 to 4, that region is the solution set. And that's really all there is to that. I'm going to work some other examples, but that is the process. They're all just like that. You solve the quadratic either by the formula or by factoring, the method you like the best, and then take a test point from each region that creates to see what works. Now, if you're using your graphing calculator, which is allowed in class, you just can't program it with formulas and use that, but you can use just the regular features of your graphing calculator. Know that this is graphable. We are going to, in Chapter 2, we're going to be graphing all the time. We're going to merge into graphing these, and we'll say that equation equal to y. So if you use your y equals feature and you graph this equation, we're going to learn in the next chapter that that is a parabola. Any quadratic equation graphs to look like this U kind of shape called a parabola. So if you want to take time to type that in as y equals, and that you'll see the parabola shape show up on your graphing calculator. And again, this will be how we'll do it later. And where it cuts the number line, -3 and 4, those are your solutions to your quadratic. And then if you're looking for less than 0, you want the part of the parabola that's under 0. So 0 would be, you know, the x-axis. So the part that falls under 0 is going to be this from -3 to 4 region. If you want the part greater than, like the one we're getting ready to do next, it'd be this part that's above it. These two outer regions will be your solution. So you can, that's optional, but I just wanted to mention it to you and also to kind of get it in your mind so when we see it later. So if I'm doing a greater than problem, it's going to be these two outer portions. It's going to be this region plus this region. It'll be two parts there instead. So it's either in the inside or the outsides. Just because the nature of this, it's a parabola. They don't tell you that in section 1.7, but I'm just kind of giving you that ahead. Heads up on that is that quadratics graph to be U-shapes. So that's why it makes 3 regions. 1, 2, 3 regions. And your solution set will either be the inside, the middle of it, or it'll be the two outer regions because of the shape. All right, let's moving on. You know, I always like to give you a U try. I think, though, before I do, we'll do a greater than, so we'll have one of each to see the difference there. Okay, example 6. Another quadratic equation. This time we have a greater than or equal to 0. Okay, so remember we solved this quadratic. If it's not in standard form, you need to move it across your lines, you know, get it in standard form, and then you can A, B, and C it if you like the quadratic formula. But this also is factorable if you want to work it that way. And so notice that it factors to be 2x minus 3 and 1x plus 4. When that's FOILed, it will give you this quadratic. Then setting each parenthesis equal to 0 by the 0 factor property, we can solve and get 3 over 2 and -4. So our two solutions to the quadratic, which just makes a boundary line on our number line. That's not, we're not finished when it's an inequality. We've got to follow up and think of it as cutting the number line or the x-axis at -4 and 3 over 2. And then we have to figure out, is it these two outer regions or the inner side, inner part of the region? It'll be one or the other. So what I like to do is just take my test point of 0 because it's the easiest number to work with, you know, of all the numbers. So I take the 0 point, find where 0 would be on this number line, and it's between the -4 and 3 over 2, and test that one in the original problem or in its factored form. I suppose you could do that as well. I'm going back to the original problem though, and I'm plugging in x is 0. And I'm going to say, well, does it work? Is it yes or no? If it's yes, I'm going to shade. So this would be a 0 plus 0, so just minus 12. And we're asking, is -12 greater than or equal to 0? And it is not. So I should not shade where that test point was. Now, if I was real careful and I'm feeling real confident that I did that carefully, then I say that doesn't work, so it must be these two parts. So I'm going to shade the two outer regions. To be absolutely sure, and the book's recommendation is you do your test points. Like put in -5 for the x's, make sure it works. And then take something out of this region, like +1, +2, make sure it works. But to save time, I'm just going to say I've ruled out that it's not the middle, so it must be the two ends. Now, how do we write that in interval notation? Notice I have a line under this, so these should be brackets. We use brackets when we have a line under it. Typically, that means you include the endpoints when possible. So we have two regions. We have -infinity to -4 with a bracket and parenthesis under infinity. And then we put a U for union. It means there's two sections, so we U to say there's another section, or plus 3/2 to positive infinity. And that would be your final answer. Okay, now I'm going to give you a U try. So if you want to write this down and then pause the video, I always want you to do that. You will be a stronger student if you practice as we go along. Okay, so the problem for your U try, 3x squared minus 11x minus 4 is greater than 0. So this is factorable, as most of these are, like I mentioned earlier. 3x times x to be 3x squared. I need the signs to be different, to be a -4 on the end. I'm going to put a 4 times 1. A lot of times it's 2 times 2, but this actually needs a 1 times 4. Check it out. That would be 1x in the middle and -12x for the outers, which would combine to be -11x. So that does work and FOIL correctly. Set each part equal to 0 to get your boundary lines. We get a solution of -1/3 and +4. Those are just boundary lines, so we're not done yet. So we've got a -1/3 where it cuts the number line and a +4. We want to know whether to shade the middle or the two outer sections. So I like to check 0. Sometimes 0 is between your two numbers, or sometimes it's off to the side. It depends on your solutions, but the ones we've seen, we have a negative number and a positive number, so it's definitely zeros between those. And then I check 0 either in the factored form or original form. That's up to you. I'm going to the original form. I'm plugging in 0 for my x's, and you can kind of just say it's going to 0 anything with an x in it, so you can kind of just mark those out and say it's -4. Is -4 greater than 0? And no, it is not. So we do not shade the middle, so that means it's the outer sides, these two sides. So parentheses, because there's no line under this, these should be all parentheses. So this will be -infinity up to -1/3 with a parenthesis, and then union or plus this region of +4 to positive infinity. And that's your final answer for that. Okay, I think that's a good stopping point for us to move on to the next video. The next one will address the fraction inequalities. So this was the quadratic. We got one more type of inequality to study, so I'll be right back.